Okay, picking up where we left off, we're going to do one more example of a test of significance for a mean. All right, I'm looking at letter E in your outline. It says obesity raises heart attack risk, according to a study published in the March 1990 issue of the New England Journal of Medicine. Those about 15 to 25% above desirable weight had twice the heart disease rate. Suppose the data listed below are the percentages above desired weight for a sample of patients involved in a similar study. Give us the data, okay? It's percentages that are not labeled each as percentages, but it does tell us that they are percentages, okay? But this is quantitative data, okay? So we're still treating it like quantitative data. Percent is just the units for this quantitative data. Is there evidence to conclude that the mean, that's important, mean percentage above desired weight is not 18%? We're going to come back to that, is not 18%. Use a 2% significance level. Okay, lots of things here that we haven't seen happen before, but the general premise is still the same. We're studying a claim about the mean, trying to prove whether that claim is true or false, okay? And we are going to be getting our standard deviation from this set of data here. So it's going to be a sample standard deviation, or in other words, an S. So when I say that I'm doing a significance test, it's about a mean. I know that my standard deviation is a sample standard deviation. All of that leads me to know that this is a t-test. Okay, I'm going to be using a t-score. So I'm going to start by defining what's the variable that we're studying. We're studying mu, true or population mean, percentage above desired weight. True, mean, percentage above desired weight. Okay. And then before I get into my conditions, I'm going to look at my hypotheses, my null hypothesis and my alternative hypothesis. So our null hypothesis, remember, that's innocent until proven guilty. And the way that the question worded here says, is there evidence to conclude that the mean percentage above desired weight is not 18%? We're going to try to prove that it's not 18%, but at the get-go, we have to believe innocent till proven guilty. So we have to start with the assumption that the mean is 18% or is equal to 18%. Your null hypothesis will always say equals, okay? Because we start with the assumption that there's some value that is true, and then we have to prove something about that value. Okay, and then you might ask yourself, like, these are percentages. Do I need to change them to decimals? Since percentages are just the units, we don't have to convert everything to decimals, okay? If we were studying a proportion, then we would want to do our calculations in decimal format. Okay, and then our alternative hypothesis here is one that we haven't seen yet. It just says is not 18%. So we don't really care necessarily if it's more than 18% or less than 18%. We just care if it is or isn't 18%, if it is or is not 18%. So we are going to do our alternative hypothesis is that mu is not equal to 18. Okay, and now I'm going to jump into my conditions. Hopeful that it said random, but I don't remember that it did. It says that it was a sample. It does not say that it was a random sample, so that's a bummer. Okay, not given randomization. Gonna have to remember that for later in the problem. Okay, I'm gonna check normality here, and my sample size is not 30. Let's see. 13 is 26, 27. It's close, but it's not quite 30. So we can't use central limit theorem. Never tells us that it's normal, so I'm going to have to make a graph. Okay, I'm going to need my data in my calculator anyway, so I'm going to take a minute and put that into my calculator. Remember, that's stat edit. Okay, and all of our values go in L1. So I'm going to go ahead and put all of those in. Okay, I've got all of my values in. There's 27 data points. Pause the video if you need to finish getting your values in your list one. But I'm going to go make my graph. So I'm going to go to second y equals Turn my plot one on, choose whatever type of graph I want so that I can check the shape, whether that's a histogram, a modified box plot, or a normal probability plot. I tend to like to look at histograms because they show shapes clearly. And I'm going to graph. Oh, I've got a cube root function in there from algebra. I'm going to get rid of that. Okay. And I'm not seeing my graph, so I'm going to go to zoom stat. And there it is. Not loving that. I think this 27.7 is my outlier up here. Okay. But it's definitely not even close to looking normal. So I'm going to sketch this down. Okay. So again, another condition not met. Sample of weight percentages. Is skewed left with a high outlier. So normality cannot be proven. And then, let's see. Sample of patients involved in a similar study doesn't really tell us a whole lot more about the criteria that they used. So we just know that they're overweight patients. There were 27 in our study. I'm sure there was probably a population of 270 that they pulled those 27 from. Okay, that's our independence assumption. Assume the population of available patients is at least 270, so samples are independent. Okay. Now, we've got all of that done, although not very well. Randomization and normality were problematic. We'll come back to that. Okay, we are going to calculate our t-score so that we can get a probability. So if you remember, our t-score is basically the same calculation as a z-score. X bar minus mu divided by, but instead of having the population standard deviation, we have the sample standard deviation. So it's S over the square root of N. We'll fill that out in a minute. Get our t-score. Along with our t-score, we're going to need our degrees of freedom, which is N minus 1. So it will be 26. Okay, and then that will give us our probability value as well. Okay, so for our t-score, I know that my assumed mean is 18%, and I know that N is 27. I don't at the moment know X bar or S. We have a couple options for how to get those, okay? So of course, we could go to stat calc and we could get it in one variable stats. That will have X bar and S. Or I can just wait until I actually go do the t-test, which is what I'm going to do now, okay? So I'm going to go to stat test t-test. And it's going to ask me, do you have data or stats? Since my data is in L1, I'm going to go ahead and choose data. And it's not going to ask me for as many things. It's just going to say, okay, what's your null hypothesis value? Ours is 18. Okay, that's from our null hypothesis there. Is your list L1? Yes. Is your frequency 1? Yes. And then it's, what is our HA? What's our alternative hypothesis? And in this case, it's not equal to. Okay, so I want to show you something about when we choose this not equal to option, okay, or when our alternative hypothesis is not equal to. So I'm going to use this draw option. Hopefully it will kind of illustrate this for us so you can see how this is different. Okay, here's our normal distribution. And when our HA is not equal to, we don't have a preference on whether we're looking for the lower end of the distribution or the upper end of the distribution. In fact, we're looking for both of them. So as you can see here, the probability is actually shaded on both ends of the t distribution here, okay? And we've got our t-score and our p-value there. We'll come back to those. We'll do this again in just a second. But I wanted you to see that when your alternative hypothesis says not equal to, your p-value, your probability, is the probability on both ends of the graph, okay? So let's go back and run the t-test again. And this time, we're going to choose the calculate option because it's going to give us some things that we've been missing. So like we said before, you could have gotten this x bar and this s already from one variable stats, but I like to just get it all at once. It's a little bit less work, okay? So our x bar is 19.278. 278. And our standard deviation is 3.436. And that t-score that resulted was 1.932. And then we're going to talk about this probability here in just a second, but I'm going to get my t-chart and we're going to talk about how this works again, because it's something that we seem to forget easily. So degrees of freedom 26, t-score of 1.932, okay? So degrees of freedom 26, and I'm looking for a t-score close to 1.932. Okay, so I can see here that 1.932 is going to fall between 1.706 and 2.056. So if I follow those to the top, I'm going to see that my probability, the tail probability, is supposed to fall somewhere between 0.05 and 0.025. But then when I look at my calculator, I go, wait a second. The probability from my calculator says that it's 0.064. 0.064 does not fall between 0.05 and 0.025. But look at this distribution up here and what is shaded. Only one side of the t distribution is shaded on our chart. So this tail probability is only one side. And we know that because our alternative hypothesis was a not equal to, that we really need both sides of our distribution shaded. So my chart is always giving me one side, which is okay for a less than or for a greater than, but when it's a not equal to, I need to double these values on my chart to make sure that I account for both sides of the graph. The calculator, because we told it not equal to, already knew that it needed both sides, and so that probability value is already including both sides of the graph. Okay, so I'm going to write a couple things down and I want you to kind of see this. So if I'm asking you to find the probability based on your chart, you would initially go to your chart and go, okay, it's between 0.025 and 0.05. So you might write that like this. My probability value is somewhere between, and then we're going to put our lower number, 0.025 and 0.05. But then you're going to go, hold on. Because my HA says not equal to, that means that these two have to get doubled because I need both sides of the distribution for my probability. So in reality, my probability should be between 0.05 and 0.1. Okay, so that's finding the p-value off of the chart. Now, truthfully, you're not asked to do that super often. Most of the time, you're good just taking the probability value straight from the calculator and calling it good, okay? So the exact probability value is 0.064, like we've already said. Okay. These two should always agree with each other. Okay. Your probability from your chart and your probability from your calculator should always agree with each other. And then there's one other thing that this problem does differently that we haven't seen before. It says use a 2% significance level. That's the alpha, or kind of the cutoff for where we are able to say reject or fail to reject. And typically we assume that it's 5%, especially because a lot of times we're not told, we just use 5%. But in this problem, we are specifically told to use an alpha of 0.02. So I'm going to say alpha equals 0.02. And then I'm going to look at this probability value, and I'm going to look at this significance level of alpha. I'm going to go, okay, this probability, it's small, but it's not smaller than where my cutoff, my significance level is. So yeah, it's a small probability, but it's not small enough for me to be able to say guilty. Like, it's not a shocking enough probability that we're going, whoa, I definitely don't believe this. So as of right now, we're kind of still on board with the null hypothesis. So we are going to say, let's see if I have room for this. We fail to reject. We're saying not guilty. We fail to reject the null hypothesis since our probability value is greater than our significance level. And then a reminder, the second sentence is always more contextual, more understandable for someone who doesn't know AP stats. We're going to say whether or not we were able to prove our alternative hypothesis, and we were not. Okay, our probability was not small enough for that. It wasn't what we call statistically significant. Okay, when our probability is smaller than alpha, that's what we call statistically significant. That's like, whoa, super surprising. Definitely going to be able to bring this evidence to the court, and they're going to be able to rule guilty. Okay, we weren't able to do that on this one. So there is not enough evidence to believe the true mean percentage above desired weight is, we could say not equal to, is different from 18%. I'm going to say is different from 18%. And then I'm out of space, so I'm going to write it at the top. We need to address our conditions being not met, 1 and 2. Okay, so I'm going to come up to the top here, and I'm going to say since randomization and normality were not proven, this conclusion, we don't want to say interval because we didn't make an interval. This conclusion may not be accurate. Remember, that's just our disclaimer saying I needed to check these things ahead of time, and I did, but they weren't able to be checked. All right. Okay. Let me know if you have questions, and I will do my best to answer them.